In this video, we'll talk about estimating and using different variance components that we discussed in the random effects ANOVA model to get more insight into what's actually going on with those factor levels. So for estimating the variance components, we had these population values that we used before. So we had the expected value, the mean squares treatment is the sigma squared plus n, the number of replications, times sigma squared sub a. And again, you could use capital J in place of n if you wanted to use that alternate notation. Now for the expected value, the mean squared error, we had just sigma squared. So actually what this is the error variance, and the expected value of the mean squared error is the error variance, the population error variance. And the expected values of mean squares treatment is the population error variance plus the stuff that has to do with the variability of the treatment effects within the population of factor levels. Now for the sample values, or the estimated values from data, these are going to be pretty similar actually. The estimated value of the variance of the error is just the MSE. So we use the MSE as a point estimator, and actually because the expected value of the MSE is sigma squared, this is an unbiased estimator. So recall that the use of hat over a Greek letter is saying that this is the estimated value from the sample. Sometimes we also use S, so S squared equals MSE is another thing that you'll sometimes see, or sigma squared hat. Now for the sigma squared sub a, so how do we look at the variance component of the variability that has to do with the treatment levels, the treatment effects? Well, pretty much what we do is we come up here to this expected value of the mean squared treatment and solve for sigma squared sub a. So if we do that solution, recall n is not the total sample size, that's capital N, little n is the number of replications per factor level. Again, also J in that alternate notation. And I keep repeating that because that's coming up here where we'll use that. But the sigma squared sub a hat is going to be the mean squares treatment minus the mean squared error over n. And again, these are the sample mean squared error, the sample mean squared treatment, the sample mean squared error in these calculations to get the variance component estimates, the predicted values for those. Of course, these are not going to be completely correct, but we're hoping that these are pretty close. So the ANOVA variance components are what we call moment estimators, and normality is not required for these. These variance components estimates are unbiased estimators, and actually this is pretty huge. That idea that sigma squared hat is the MSE, that's used in all of statistics. That's used in regression. That's used all over the place. So the fact that these are unbiased estimators and these estimate effects, specifically the variance of the error term, that being the mean squared error, that is used very, very often. Now, finding confidence intervals on the variance components is clumsy. We'll show one of the confidence interval calculations on the next slide, but in general, it's and negative estimates can occur. So when I'm actually dealing with real data, sometimes you get a negative estimate for the variance. And this is kind of embarrassing because variances, it's sigma squared. Variances are always squared. And so because of that, they're all non-negative. Variance is always a positive number. So when you get a negative estimate, you know that that's wrong. What that's really saying is it's estimated to be very, very, very low, close to zero. So confidence intervals, error variance, again, I mentioned we can calculate them, but they're clumsy. For the error variance, sigma squared, we'd have the capital N minus 1, so that's the total sample size minus 1 times the MSE, and then we divide by a chi-squared. Note that the chi-squared in these different cases just depends on, the chi-squared in these different cases, the only thing that changes is the alpha levels in these different chi-squareds. And actually, I just keep making typos all over the place. I actually think that these are backwards. I think that this should be 1 minus alpha over 2, and that this should just be alpha over 2. So I apologize about that. And recall, chi-squareds only have a single degree of freedom term. So we have capital N minus A degrees of freedom, which is the same degrees of freedom as our error term. And actually, if you want to work that out, if you take the degrees of freedom for the error term A times N minus 1 and just distribute in the A, you'll see that that is equivalent to capital N minus A. All right, well, let's look at a textbook example and see kind of how this can be used in a practical way. So in this particular case, we've got a textile company that's looking at looms, and we're trying to look at variations between looms and look at the strength of different fabrics that came out of these different machines. So we've got four. These are our factor levels. We've got one factor loom with 4 different entries, 4 different machines. And then we have 4 observations within each machine. And again, each of these observations are independent. I'll make my typical note that normally we have this organized vertically, not horizontally. But in the calculation, I'm going to kind of skip over a lot of the stuff, but what I do want to focus on is the calculations that are going on here. The sigma squared component, so this is the factor effects variance estimate. This is the variance of the factor effects is 6.96. The total variance is 8.86, so that's the total amount of variability. And then the variability due to error is 1.90. So what you see when we get these variance components that is pretty nice is that we can break down the total variation into these different pieces. So we say the total variation is 8.86, 6.96 comes from the different looms, and 1.90 comes from the error. Why is this helpful? Well, again, I don't really care about these 4 machines. I just want to know, is loom important? So loom is important for 6.96 out of 8.86 of the total variation. And that lets us say conclusions like what we see here. Most of the variability of this 8.86, that's the total amount of movement, 6.96 of that movement is from the changing in the different machines, and 1.90 is just from kind of random white noise. So we're able to say something like the variance component having to do with loom is attributing or is responsible for most of the differences in the different observations. Note that we can of course, when we're interpreting this, we want to make sure we have a statistically significant value, because that statistically significant value is what's going to give us information to say, yes, we believe this is true, not just for the sample, but for the population. So recall with our interpretation saying, well, most of the variability is coming from the loom, not the white noise. Well, that's good, but that doesn't really mean much unless we have evidence to say that's true, not just in the sample, but the population. And recall that that's what our statistics are doing, is saying that's true not just in the sample, but it's true in the population. So again, here, notice that we're not talking about any individual loom. We're not really looking at means in any individual loom. We're looking at the variance component as part of the total variation of the data. What component of that is due to the varying machines? What component of that is due to the changing of machines? And that's what we're looking at. So this is kind of a single number that represents all of the different looms together. And that's why we like to do this when we don't care about the particular machines, when we're just trying to look at the machine effect, because we don't have to look at the individual means. For another example, again, consider the idea of judges rating perhaps a movie or an ice skating person, figure skating person. We don't really particularly care about the judges. We just want to see what the skater score is, but maybe we want to look and see, do the different judges have a different effect? Are some judges just more harsh than other judges? And we could do something similar where we have the judge effect on the total score variation. And in that particular case, we may want it to be small. We may want there to not really be a large judge effect in a case like that. So actually, when we're looking at how do we determine large or small, One useful statistic is called the intra-class correlation. Now, this statistic estimates the percentage of variation that is due to the variance between the groups. And so in this, you'll see that the denominator is the variance of y. So let's look at the equation. The intra-class correlation is the variance of the treatment effect divided by the total variance, the variance of the treatment effect plus the variance of the error. So the variance of the treatment effect divided by the total variance in the outcome. So pretty much what we're doing is we're saying what percent of the total variance in the outcome is the variance of the treatment effect. And this comes out as a proportion. Of course, you multiply that by 100 to get a percent. But this calculation gives us an estimate of the proportion or percentage of the total variance that is due to the treatment effect. And this is a really nice statistic because you can say, well, hey, around 80% of the variance in the different textile strengths is due to the loom, and only about 20% is unexplained. And again, this doesn't have to be a good or a bad thing, right? Maybe we wanted all the looms to be really similar and are kind of bummed that the looms are responsible for a huge portion of the changes in fabric strength. Maybe that's not something we wanted, but it is something that we can use, and this statistic can be really helpful to contextualize what these numbers mean. Earlier we were kind of comparing, and we were saying, oh, look, this one's 6.9 out of the 8.8 total movement. Isn't that kind of high relatively? But being able to calculate the intra-class correlation gives us kind of a percentage number, which is a little more straightforward to interpret. Now we can also calculate the confidence intervals of this. Now what's funny is the confidence intervals we calculate with the low and an upper, and this formula looks really simple until I tell you what U and L mean. So L is this big nasty formula here, and then U is the exact same thing except we just change the alpha level of the formula. So these different formulas, you would calculate L and then U, and then you would plug them in, and that gives you a confidence interval for the intra-class correlation. And again, what is this? This is the percentage of the variation, the total variation that is due to variation in the treatment effect. And this is really nice because, again, we don't really care about individual means and treatment effects. I'm not going to do box plots here because I don't care about the individual levels. What I do care about is what portion of, or how big of a deal is the differing factor levels. So the whole purpose of a random effects ANOVA analysis is just to see, is factor level important? And the idea of the percentage of the total variation of data is due to the factor level is a really, really attractive summary to tell me intuitively, is factor level important? And this is one way to get an interval on that. Oh, and I have a note here just to remind you again that lowercase n is not the same thing as uppercase n. So when I use lowercase n, that's not the sample size here. That's the sample size within level of the factor. It's a very different thing. Capital N is the total sample size. Lowercase n is the sample size within that factor level. So this is the number of replications that we have per factor level. And again, that's a capital J in our notation. Capital N, that's our total sample size, and that's what we'd be looking for total sample size. All right, well, now to go on a bit of a tangent, estimating the grand mean. This is really a bit of an aside from what we've been covering. I didn't really know where to put this in, but it's actually recently been pretty useful. I was working on a project regarding COVID data, and what I was asked to estimate wasn't the variability of different levels. It was actually to come up with a grand mean of, like, in this particular case, how many positive tests were we going to have? And there were a couple of different things and different levels, but that's not what we're trying to estimate. We're trying to estimate the total, or the average value. So in this particular case, what we're trying to estimate is capital mu, or excuse me, is mu, that grand mean value. And the estimate for mu is just going to be what you may guess, the sample grand mean, y dot dot bar. Now the variance breaks down not too bad, actually. And this is where I'm going to switch to the IJ notation. So again, A and capital I are the same letter, and J and lowercase n are the same letter. So make that note if you haven't been following along or haven't been following that when I've been doing that. The reason I do that is because the subscript a gets confusing when I have a's everywhere else too. So I'm going to sample all the, this I from 1 to capital I is all of the different factor levels and all of the different replications within factor lists. So this is just our normal stuff in terms of what we're doing. But this is kind of the sum of squares total divided by capital N, which is also I times j. So capital N down here is what you can read I times j as. And so again, this is our sum of squares total, and we know that the variance of the sum of squares total is j times sigma squared sub a plus sigma squared, which is just the mean squares treatment. So the estimated variance of y bar is the mean squares treatment. Now, if you have seen the breakdown of confidence intervals, I guess I'm not sure if you've seen that or not. If you have, recall that the breakdown of confidence intervals is just the point interval plus or minus the critical value times the standard error. If you haven't seen that, then don't worry about it. But this confidence interval is just the same. We've got the point estimate plus and minus the critical value times the standard error. And gosh, you just see all my typos, and I very much apologize, but this should be a plus on the top end here. Y dot dot bar plus t sub alpha over 2. And in this particular case, again, you see that the standard error is the mean squares treatment divided by ij and the square root of all that. So this is our confidence interval for the grand mean. This is the mean across all of our groups. And again, there are times when this actually becomes more important than knowing a mean of any individual group. In fact, the mean of every individual group is something you may have, but you want to combine all of that to get a better or more accurate estimate of what is the overall grand mean. And this is one of the ways in which you can do that. All right. Well, in the next set of videos, we're going to start talking about something a little bit different, where this kind of closes at our random effects ANOVA. So we'll be moving on in the next set of videos to talk about assumptions, and then we'll move on to things like post hoc testing and power and all this other fun stuff, which will close out our very long chapter in this chapter where we're talking about one-way ANOVA. I think it's the longest chapter we have in this class. So look forward to that in our next video.